two topics, mainly about the different coordinate systems, and we have started about the potentials. Okay, so these are the topics that we have seen it in the last session about the different potentials what we have. Okay, so the relation between potential and electric field, we have V equal to minus integral of E dot dl. So in generalized form, we can say it as potential is the product of electric field and distance. Okay, also we can have the potential equal to Q by 4 pi epsilon R. These are the things what we have, and we have seen about the problems relating with the potential. And the simple relation between electric field and potential is E equal to minus del V. Okay, so in the last class I have told you about that relation. So the negative gradient of potential is what we call it as electric field. Negative gradient of potential is what we call it as electric field. Okay, negative gradient of potential is what we call it as the electric field. That we have seen it on the last session there. So later on we have seen about the problem relating with that potential. We have also seen about the problem with the potential there. You are relating electric field and potential, and seen about that equipotential plots. We have seen about that equipotential plots also, and the EQ spaced plots. Just I'm revising what are all we have seen on the last session. So utilization factor also we have seen, and the electric potential due to circularly charged disk. Okay, so V equal to rho s by 2 epsilon to root of h square plus r square minus h. This what you have seen there. And the dipole also we have seen electric dipole, potential due to electric dipole. Now you will be seeing about the conservative field. Okay, so any electric field we have that conservative field. So what is that conservative field? Okay, so conservative field is nothing but, so if in any field there is no work done to move a point charge from that place, we call that field as the electric field. Okay, so when potential is zero, in that equation, what we will be having that we have the generalized equation. We can see with that box V equal to minus integral E dot dl. Okay, so in that I am substituting V equal to 0. How I can substitute that V equal to 0 from the above statement? If there is no mechanism by which an energy represented by this work can be dissipated into the field, or the mathematically we can say that work done to require a move point charge around the closed path in static electric field is 0. That means V equal to 0. If I substitute V equal to 0, what happens? Closed integral of E dot dl equal to 0 there. Closed integral of E dot dl will become 0. Okay, so in exam point of view, they will be asking you, they will be giving you an electric field and asking you to find whether it is conservative. Find whether it is conservative. So what we have to do? We have to take the dot product of that vector and we have to take the line integral. If you are getting the answer as 0, then we can say the total electric field around the closed path is 0 for that conservative field. Okay, was a closed integral of E dot dl equal to 0. That's what you will be having there. Okay, then the basic concept about current and current density. In the basic physics, you might have studied about the current, rate of flow of charges. So I equal to dq by dt. And current density will be represented by J. In some of the book they will be represented as K. Okay, so current per area. Current per area is what we have it as current density. So J equal to di by ds. J equal to what we will be having? Di by ds. So from that we can write I equal to closed integral of J dot ds. Closed integral of surface to J dot ds there. Already know the concept that unit of current is amperes. Unit of current is amperes. So with the depth concept of current, we can have that statement. If 1 coulomb charge crosses the reference point in the circuit within 1 second, then it is assumed that one current of 1 ampere is generated. That is a depth point of current statement. Simply we are saying that it's a ratio of dq by dt, rate of change of charges. So in the depth concept we can see that one coulomb of charge within 1 second, if it flows within the 1 second, 1 coulomb of charge, that value we can say it as 1 ampere. That value we can say it as the 1 ampere. So then as per J equal to dI by ds. Then this is the point form of Ohm's law. We know that Ohm's law, potential difference across the conductor is equal to the directly proportional to the current flowing through the conductor. That V is proportional to I, and we are inserting a constant, what we call it as R. So V equal to IR. That is a basic concept we might have studied in the Ohm's law there. So with the electric field concept, we can relate with the Ohm's law there. Current density is directly proportional to electric field intensity. Current density is directly proportional to what will be having as electric field intensity, and the proportionality constant, what we can have it as sigma, conductivity. Sigma is called as a conductivity. So in an exam point of view, they ask point form of Ohm's law is it's nothing but J equal to sigma E. J equal to what will be having sigma E, where J is called as a conductivity and E is called as a electric field intensity. And E is called as the electric field intensity. So J equal to what will be having sigma E. The next one, electric field in free space. Electric field we have in many materials. In free space, in conductors, in dielectrics, we have that electric field. So when you see about that electric field in free space, so this is the standard formula for electric field. E equal to Q by 4 pi epsilon R square into AR vector. We know about that epsilon. Epsilon is nothing but the product of epsilon naught and epsilon R. Epsilon equal to epsilon naught and epsilon R. So in free space, what will be having? Epsilon R equal to 1. Epsilon R equal to 1. So hence we have electric field E equal to Q by 4 pi epsilon naught R square into AR vector. R square into AR vector. So epsilon R equal to 1. So straight away I am substituting epsilon naught. So when you go for the test, conductors in static electric field. Conductors in static electric field. So a conductor, we can say it as the infinite number of charges that are mainly free to move there. A perfect conductor will be having conductivity of infinity. A perfect conductor will be having conductivity of infinity. It will be having more conductivity, and it will not have any electrostatic field within it. That's an important statement. It will be distributing the electric field throughout the area. It will not contain all the electric field within it. So we can say the conductor as the equipotential body. We can say the conductor as the equipotential body there. So we already know that E equal to minus del V. E equal to minus del V. So if you substitute E equal to 0, what happens? Del V will become 0. So under static condition, what happens? E equal to 0, that rho V will also become 0. Then potential VAB will be 0. That is, inside the conductor there won't be any potential. Only at the outside the network you will be having the potential. The important concept, but you have to keep it in mind. Then if you go for the resistance of the conductor, already you know about that concept that E equal to V by L. Electric field is given by potential by distance. So let us assume the conductor, you can see that one. It is applied with a voltage V and the current I is passing through the conductor. An electric field will be produced around that one. You will be having that one. So we can have the relation of resistance along with the electric field here. The point form of Ohm's law is J equal to sigma E, and current, you can have it as current density into area, that is J into S here. On solving, equating the two, you will be getting R equal to rho L by S. Rho is called as the resistivity. Rho is called as the resistivity, which is the inverse of conductivity. Which is the inverse of conductivity there. Now you will be getting that R value there. So R equal to V by I. So how we can relate V? V equal to that minus integral of E dot dl. So neglecting that minus sign, can have it with the E dot dl. Similarly, I is what we have it as surface integral of J dot ds. Surface integral of J dot ds. That is nothing but J equal to sigma E. You know about that one. J equal to sigma E. So sigma E into ds. Okay. Now the polarization, we come across the next point, what we call it as a polarization. When you see about dielectrics in static electric field. So you know the difference between conductor and dielectrics. Mostly it lies on the availability of electrons on the outermost shell. That what we have it as the dielectrics. That gives the main difference between the conductor and dielectrics. Okay, so in any if you have applied more amount of electric field on the dielectric, it will turn as the conductor there. It will turn as the conductor there. That's the point what we'll be having there. That's a product dipole. Two charges separated by the small medium, what we call it as the dipole here. That it consists the dipole, and the product dipole moment is nothing but the product of charge and distance. Product of charge and distance, what we call it as the dipole moment there. And the polarization we can represent within the form of that product of charges into that is dipole moment into L dash, where it is called as net dipole moment per volume. Net dipole moment per volume then. Okay, so we can also relate the flux density with the polarization part. Flux density with the polarization part. So D equal to epsilon naught E plus P. Normally D equal to epsilon E. So in the last classes we have seen the relation between flux density and field intensity. D equal to what we will be having? Epsilon E. Okay, so D equal to epsilon naught E here. D equal to epsilon naught E. Along with the polarization concept, we have that D equal to epsilon naught E plus P there. So here we term a new term called as a susceptibility, electric susceptibility or dielectric susceptibility. Okay, so P equal to epsilon naught E into that dielectric susceptibility. We have that relation of that one there. We can see that one. D equal to epsilon naught E into polarization concept. What we have that 1 plus susceptibility, we can have that one. Okay, so epsilon R equal to, how we can relate this thing? Epsilon R equal to 1 plus dielectric susceptibility. Dielectric susceptibility. Okay, so from this concept, we have that one. Polarization. If you substitute that polarization P value here, you will be getting D equal to epsilon naught E plus susceptibility into epsilon naught E. Taking that epsilon naught E outside, you will be getting these things here. You will be getting D equal to epsilon naught E into 1 plus susceptibility. So you will be getting D equal to epsilon R E. Already we have separately D equal to epsilon R E. Then substitute the thing, you will be getting epsilon R equal to 1 plus dielectric susceptibility. Okay, so now we are seeing about that model problem relating with that polarization, where we have to find out the magnitude of D. Magnitude of D, and they are given with E value and dielectric susceptibility. And we also have to find out the polarization. We have to find out D, flux density and polarization. They are given with the electric field and dielectric susceptibility. You know the concept that D equal to epsilon R E there. Okay, epsilon naught is constant 8.854 into 10 power minus 12, and E value is given in the problem 0.15 into 10 power minus 3. But we don't know about epsilon R. Just now we have seen that formula, how you can find out epsilon R. So epsilon r equal to 1 plus dielectric susceptibility. 1 plus dielectric susceptibility. If you apply that one, you will be getting epsilon r value there. Okay, you know about that polarization concept there. You know about that polarization concept. Apply that one. So you will be getting polarization formula. Dielectric susceptibility into epsilon naught E there. D value you know, P value you know there. Okay, so the second model problem we can see where we have to find out the polarization of dielectric materials. Where we have to see the polarization of dielectric materials. Okay, they are given with epsilon r value and D value. They are given with epsilon r value and D value. You want to find out the polarization. Okay, what is the polarization formula? It is actually dielectric susceptibility into epsilon naught E there. Okay, and D equal to the problem they are given with D. So we have to find out E first. Then dielectric susceptibility we have to find out. Okay, with that we can find out the polarization here. What is the formula for a dielectric electric field? D equal to epsilon naught epsilon r E we are having. Already know about E. Sorry, already know about D. If you substitute, you will be getting E value there. E equal to D by epsilon naught epsilon r. So the electric field E equal to D by epsilon naught epsilon r. In that you will be getting E value. Then P value, it is dielectric susceptibility into epsilon naught E there. We don't know dielectric susceptibility. For that, first we are finding out epsilon naught there. Dielectric susceptibility, we don't know that. So for that, known about epsilon r value, relative permittivity, apply that value, you will be getting that dielectric susceptibility there. Okay, and you will be getting that polarization concept there. This is about the thing about the polarization and electric field. So the next one, what we can have it as electric field in multiple dielectrics. Okay, so electric, what is, how will be the electric field in multiple we have multiple dielectrics, linear, non-linear, isotropic, non-isotropic, homogeneous dielectrics like that. In all the thing, how will be the value of that E and D there? That we are going to see now. So when you say that dielectric as a linear dielectric, when you can say the linear dielectric as linear dielectric is when flux density varies linearly with E. When flux density and field intensity varies linearly. When flux density and field intensity varies linearly, we call the dielectric as a linear dielectric. We call the dielectric as the linear dielectric. Then next one you will be having homogeneous dielectric. Homogeneous dielectric. So in homogeneous dielectric, what you can have? So here we can say the dielectric as homogeneous dielectric when epsilon r sigma, that is conductivity, which does not vary with the region we have enclosed to them. Okay, so they call it as a homogeneous dielectric. Non-homogeneous dielectric. So you can say it as materials, you can say it as a non-homogeneous, which is they are dependent on space coordinates. Which they are dependent on the space coordinates. The next one, what we can have it as a isotropic dielectrics and anisotropic dielectrics. In isotropic dielectrics, okay, so the material for which D and E flows in the same direction. Materials for which D and E flows in the same direction, we call it as a isotropic dielectrics. Okay, in anisotropic dielectrics, the material for which D, E, and P are not parallel. Okay, when flux density, field intensity, and polarization are not parallel, flowing in parallel, we can say it as anisotropic dielectric. Here they will be having 9 components of permittivities, what we collectively called as tensor. So this one they may ask the gate question, what is the tensor? Tensor is nothing but that 9 components of permittivities. It exists in the anisotropic dielectric. It exists in the anisotropic dielectric there. Okay, so that's also the important concept there. Then we can see with that one the curl problem. Last one we have seen the solution. Boundary conditions. We have with the boundary conditions there. So when you have the dielectric medium, we have seen about the dielectric, conductor, and free space. Last 3 divisions. So assume the boundary. We can see the boundary here, and I am placing 2 dielectric materials one over the another. And I am placing the dielectric mediums one over the another. If I place one dielectric over another dielectric at the interface of 2 dielectrics, how will be the electric field flow? How will be the flux density flow? That's what we can see there. And that too we can see for 2 components. One is called tangential component, another one is called normal component. Okay, I'm once again repeating you. So I am placing a 2 dielectrics one over the another at the interface of 2 dielectrics. At the interface of 2 dielectrics, how will be the electric field and flux density flow? That's what we are going to see now. And that too we can resolve into 2 components. One is tangential component, another one is normal component. One is tangential component, another one is normal component. Okay, so here you can see that one. So the power diagrammatic view represents the ET1 and EN1, similarly ET2 and EN2. So for that analysis, they might have taken the closed surface here. A, B, C, D, A, they will be assuming the closed surface. They will be assuming with the closed surface here. Okay, so since we have 2 different dielectric materials, I am not placing same dielectric materials. I am placing, that is very, very important. I am placing 2 dielectric materials one over the another. So epsilon 1 will be the one dielectric and epsilon 2 will be the another dielectric material. Epsilon 1 will be the first dielectric, epsilon 2 will be the another dielectric material here. Okay, so when you place one dielectric over another dielectric, what you will be getting it as their tangential component of electric field is same. Whatever the tangential component of electric field you are getting on the first dielectric, its value will be same for the dielectric 2 also. Tangential component of electric field 2. So that what we call it as continuous. That what we call it as continuous. Since the value is same, we can say it as a continuous. Okay, so here we can say that ET1 equal to ET2. Here what we can say ET1 equal to ET2. That is tangential component of electric field is continuous across the boundary. Tangential component of electric field is continuous across the boundary. ET1 equal to ET2. Now we know about the relation between electric field and flux density. What is the relation between electric field and flux density? You will be getting D equal to epsilon E. D equal to what you will be getting? Epsilon E. Okay, so from the above equation, how we can write D value? dt1 by epsilon 1. dt1 by epsilon 1. Already know about ET1, so we can rewrite this the ET1 as dt1 by epsilon 1. Similarly, ET2 can be written as dt2 by epsilon 2. And these are, since dt1 is not equal to dt2 because they depends upon their permittivity, epsilon 1 and epsilon 2. We call this one as the tangential component of flux density is discontinuous. Tangential component of flux density is discontinuous there. Only the tangential component of electric field is continuous, whereas the tangential component of field intensity is flux density is discontinuous. That is one of the thing what you are getting here. Okay, now similarly we are going it for the normal components. So when you go for the normal components, what will be having that flux density will be getting continuous and field intensity will be getting discontinuous there. So what we have to remember is when you place one dielectric over another dielectric, one dielectric over another dielectric, tangential component of, you can see this one, tangential component of electric field is continuous, whereas normal component of flux density is continuous. For that, they are assumed with this diagram here. In the boundary, we are assuming the Gaussian surface over the pillbox. And if you apply the Gauss law and if you simplify, we will be getting that concept dN1 equal to ds2, assuming the surface charge is 0 there. Assuming the surface charge is 0. So dN1 equal to dN2. What will be having that? Very important statement there. dN1 equal to dN2, which implies that normal component of electric flux density is continuous across the boundary with the condition of charge free surface. With the condition of what we will be getting? Charge free surface. The surface should be charge free. Okay, so here you will be getting, if you substitute D equal to epsilon E, D equal to epsilon E, what you will be getting? Epsilon 1 En1 equal to epsilon 2 En2. Epsilon 1 En1 equal to epsilon 2 En2. Here normal component of electric field intensity is discontinuous. Normal component of electric field intensity is discontinuous. That you can see it from here. Okay, clearly see about this part. Now we will be seeing about the thing. From that we can have the law of refraction. Okay, so with that known values of two dielectrics, with the known values of two dielectrics, that is boundary condition, we can find out this one there. Tan theta 1 by tan theta 2 equal to epsilon 2 by epsilon 1. And we can see a model problem relating with this boundary condition. Okay, they are given one vector E1 vector equal to 2ax minus 3ay plus 5az with the charge free dielectric. The diagram what they are given with two mediums, epsilon r1 equal to 5 and epsilon r2 equal to 2 here. Epsilon r1 equal to 5 and epsilon r2 equal to 2 here. So what we have to show is, we have to find out what is D2. They are given with E1, electric field of first medium. They are given electric field of first medium. By applying the boundary condition, what we have to find out is, we have to find out what is the flux density on the second medium, that is second dielectric. Okay, very interesting problem this one. They are given with electric field of medium 1. What we have to find out is flux density of medium 2. Flux density of medium 2. So you know about that boundary conditions that we have marked in red. Et1 equal to Et2. Then dN1 equal to dN2 there. Et1 equal to Et2. dN1 equal to dN2 there. Okay, so to find out this concept D2, what we can have, the formula is d tan 2 plus dN2. d tan 2 plus dN2. d tan 2 plus dN2 will be giving you the D2 value. So first I am going to find out the d tan 2, then I am going for dN2, or then we can find out this concept there. Okay, so with the help of boundary condition problem, with the help of boundary conditions, I can find out the En1 and Et1. En1 and Et1 here. That's what I am finding out here first. First I am finding out En1, then E1 is always En1 plus Et1. Already you know about E1. Now from the diagram I have extracted En1, so I can calculate Et1. So from the boundary condition concept, what we have, Et1 equal to Et2. what you have find out ET1 is a hold a minute, pa. We are seeing about this thing. Okay, so d tan 2 equal to epsilon 2 into E tan 2, that is ET2. So epsilon naught to E tan 2. Next we are finding out that dn1, epsilon naught epsilon r1 en1. You know the concept that en1 equal to en2. So from that we can extract the parts. dn1 equal to dn2. Okay, so sorry, not en1 equal to en2, that is dn1 equal to dn2. So apply the concept there, you will be getting d2 value. Already know about the dt2 and dn2. Now if you substitute, you will be getting d2 value. This is how we have to find out from the basic concept. This is how we have to find out from the basic concept. So when you place, so far we have seen about that two dielectrics. Now when you place one conductor and dielectric, one conductor and one dielectric, one over another. Okay, so for example, if you place mica and polyethylene, that are two dielectric materials. Now if you place a copper plate along with one dielectric, so at the boundary between or at the interface between the copper plate and dielectric, what will be the concept that we will be seeing here? Okay, but these concepts only lies the basic concept of capacitor. In capacitor, what we are doing that two conductors separated by the dielectric medium. Next we are going to see about capacitor only. For that, this will be more helpful. Okay, so here what you are doing that I am placing conductor at the top, and after the conductor I am placing the dielectric material. After the conductor I am placing the dielectric material. So what happens here? What happens here if you place a conductor over the dielectric material? If you place a conductor over the dielectric material, what happens is you will not have electrostatic field within in it. That's all you can see in the diagram there. So in a conductor ET equal to 0, whereas in a dielectric we will be having that ET value there. So the ET value will become as 0 there. Very, very important concept. So when you place a conductor and a dielectric, tangential component of electric field is 0. Tangential component of electric is a conductor over the dielectric. When you place a conductor over the dielectric, when you place a conductor over the dielectric, okay, when you place a conductor over the dielectric, you will be having ET equal to 0. ET equal to 0 there. Okay, so you will be having dn2 is also, it will be having with that 0 part there. The ET equal to 0. Similarly, the normal component of dn2 will become as a 0 here. Okay, so the total normal component will be equal to the charge density. Total normal component will be equal to the charge density, that is rho s. Surface charge density, what will be having it as a rho s there. dn equal to rho s there. Okay. So the next what will be having it as a Poisson's and Laplace equation. Poisson's and Laplace equation. Okay, well, so Poisson's and Laplace equation are the important concepts in that electromagnetic fields. Okay, well, so this is the thing what I have told you, del dot D equal to rho V. In the last session itself I have told you that this and all they will be asking it as a statement. What is the divergence of the flux density is? In gate question. Divergence of flux density is nothing but volume charge density. Divergence of the flux density is nothing but volume charge density rho v. Del dot D equal to rho v. Divergence of the flux density equal to rho v. And we obtain the Poisson's equation with that electric field concept. If you have E equal to minus del V, then if you apply that concept here, you will be getting that Poisson's equation. Del square V equal to rho V by minus rho V by epsilon. Del square V equal to minus rho V by epsilon there. Del square V equal to minus rho V by epsilon. Okay, so if the volume charge density is 0, if the volume charge density is 0, we will be obtaining the Laplace equation. We will be obtaining the Laplace equation there. So volume charge density is 0. So we are substituting rho v equal to 0 there. So del square v equal to 0 there. If it is del v, it's nothing but gradient. Gradient. So del square v is nothing but Laplacian. Del square v is nothing but Laplacian. So similarly, we have for different coordinate systems Laplacian formula here. For different coordinate systems, we have the Laplacian formula. Cartesian coordinate system, cylindrical coordinate system, spherical coordinate system. For all these things, we have that Laplacian concepts there. And we can see with this straight away go for the capacitance. Here, the capacitance concept, you know about that one. It's a ratio of charge per voltage. The capacitor is nothing but two parallel plates separated by the small medium. Two parallel plates separated by the small distance. What it constitutes the capacitor, the device, and capacitance is the ratio of charge to voltage. Charge to voltage here. That's potential difference. So you know about the unit of capacitance. It is nothing but farad. We are having it as farad. So here we are having that. You can see that one. Two equal and opposite volt charges. Two equal and opposite charges separated by the small distance, and it constitutes a capacitor there. The device, what we have it as a capacitor. In between we have the dielectric medium. In between we have that dielectric medium here. So in terms of electric field, how we can define the capacitor? In terms of electric field, how we can define the capacitor there? So that what will be having is C equal to Q by V. C equal to Q by V. You will be having the concept of capacitance. C equal to Q by V. Okay, then from Gauss law we can say it as Q equal to surface integral of D dot ds. Surface integral of D dot ds. Okay, Q equal to surface integral of D dot ds. So if you substitute that one, so epsilon naught into E integral E dot ds. Then potential is nothing but V equal to line integral of E dot dl. Okay, so you will be having that integral of E dot dl there. In terms of capacitance, we can see that one. So here we are neglecting the minus sign. Already we know that one, V equal to minus E dot dl. Here we are neglecting the minus sign. Okay, so because we are always having we are indicated with the absolute value of V. We are interested only with the absolute value of V. So when you go for the capacitor, we have these things: capacitor in series, capacitor in parallel there. So the cases is reverse as the of resistor. Cases is reverse as the of resistor. Cases is reverse as the of resistor here. Okay, so if two capacitors are connected in series, so the total capacitance is, if two capacitors are connected in series, two capacitance is 1 by C equivalent equal to 1 by C1 plus 1 by C2. 1 by C equivalent equal to 1 by C1 plus 1 by C2. So the total capacitance, what we can have it as C equal to C1 C2 divided by C1 plus C2. C equal to C1 C2 divided by C1 plus C2 there. Your total capacitance C equal to C1 C2 divided by C1 plus C2 there. Now when you connect two capacitors in parallel, what's the final capacitance? You will be getting C equal to C1 plus C2. So as I told, it's a reverse case of resistors. So when you connect two resistors in series, what you will be getting? R equal to R1 plus R2. When you connect two resistors in parallel, what you will be getting? R1 R2 divided by R1 plus R2. So that is a reverse case you will be obtaining here. Okay, so we'll see in that one. Take care of that one also. Take care of that one also. So the next one we can see about that parallel plate capacitor. Parallel plate capacitor. What is the capacitance of parallel plate capacitor? So when you go for the parallel plate capacitor, we can see the thing. One will be the positive plate, another will be the negative plate, separated by the small distance. Separated by the small distance. What you will be having that one? The basic thing you might have obtained for the parallel plate capacitor. C equal to epsilon A by D. C equal to what you will be having? Epsilon A by D. Where epsilon is permittivity, A is the area, and D is the distance. That's what we will be obtaining here. So here we will be derived in terms of the electric field. Here we derive in terms of the electric field. First they will be finding out electric field and using the potential concept, apply the potential concept in the electric field. We know about that C equal to Q by V. We know about C equal to Q by V. Then if you apply that one, you will be getting Q will be constant. Then instead of V, you are substituting in terms of Q, and final cancellation will have that C equal to epsilon A by D. C equal to what will be having as epsilon A by D. Okay, so capacitance is equal to epsilon A by D. Epsilon is called as permittivity of the material. A is the area of the plates and D is the distance. D is the distance there. So the next one, what we have it as a coaxial capacitor, or we can say it as a cylindrical capacitor. So we have three coordinate systems, as I told already: Cartesian coordinate system, cylindrical coordinate system, spherical coordinate system. So for the Cartesian coordinate system only, we are seeing about this thing. The last one, parallel plate capacitor. Now when you come for that coaxial capacitor, it corresponds to the cylindrical coordinate system. It corresponds to the what will be having as cylindrical coordinate system here. And what will be the capacitance of the coaxial capacitor? Same concept. First we have to derive electric field. From the electric field we have to find out potential, and from the potential we know that capacitor formula C equal to Q by V. The same concept. By Gauss law we are obtaining this one here. Okay, well, first we are obtaining the electric field from Gauss law. This is the Gauss law format. From Gauss law we are obtaining the electric field, and we know about the relation between potential and electric field. V equal to minus integral E dot dl. V equal to what you will be having? Minus integral E dot dl. So apply the concept there, and we know the V value, and you know the V value there. So C equal to Q by V. C equal to Q by V. We know that concept. Once you know that, you can find out the capacitance value. Once you solve that, you can find out that capacitance value. So what you will be getting? 2 pi epsilon L divided by ln of B by A. 2 pi epsilon L divided by ln of B by A. That is the capacitance formula here for the coaxial capacitor. The next one you will be having with the spherical capacitor here. When you see with the spherical capacitor, what is the capacitance of the spherical capacitor here? Capacitance of a spherical capacitor. Here we are having that two concentric sphere. We will be having that one circle will be having with positive charges, then another circle will be having with that negative charges. It's an example of the spherical coordinate system. Once again, we will be deriving using Gauss law the electric field and you will be finding out the potential, and finally we will be finding out the capacitance. So here C equal to 4 pi epsilon divided by 1 by A minus 1 by B. And from this we can ask with the one gate question, okay, what is the capacitance of the isolated capacitor? That means if B equal to infinity, if B is infinite, we have two radius, one with A and B is another radius B. So if B is infinite, what happens there? If B is infinite, what happens there? We have A and B, okay, so with the A we have that value and B is infinite, what happens there? So if B is infinite, what happens here? 4 pi epsilon, 4 pi, here you can see that one, C equal to 4 pi epsilon divided by 1 by A, that A will goes to the numerator. So C equal to 4 pi epsilon A here. C equal to what you will be having? 4 pi epsilon A. So that is the capacitance of the spherical capacitor, or isolated capacitor, or we can say capacitance of the spherical capacitor with outer plate is infinitely large. Outer plate is infinitely large there. So the next one, energy stored in capacitor. What is the formula for energy stored in capacitor? The basic concepts limited study in your old classes, of CV square. Same concept, of CV square. Energy stored in capacitor. Given the later on classes, you will be seeing about the magnetic field and inductors. So when you go for energy stored in capacitor, you will be having of energy density. So energy density is equal to what you will be having it as dE by 2. The product of flux density and field intensity divided by 2. It is nothing but energy density. D into E divided by 2. D into E divided by 2. What we call it as energy density. Energy stored is half CV square. The last one we have seen, energy density is half CV square. The next one, what will be having it as energy stored is half CV square. Energy density is dE by 2 here. Flux density into field intensity divided by 2 here. Okay, that is another formulas. We have more formulas. So D equal to epsilon E. D equal to epsilon E. So you will be having it as epsilon E square by 2 or D square by 2 epsilon. These are all the various formulas what we have there. Then we can see about the model problems relating with the capacitor. So we can see that one capacitor of a square metal plates 10 centimeter side. So that is actually 100 centimeter printing mistake we have. Then with the parallel plate and placed 2 millimeter apart. Space between the plates is filled with dielectric having the relative permittivity of 3.5. So potential is drop is 500 volt. What we have to calculate? Capacitance, charge, flux density and potential gradient. Okay, so capacitance formula you know, C equal to epsilon A by D. C equal to epsilon A by D. So epsilon naught epsilon R A by D. You know about epsilon naught. Epsilon R value is also, you know that the problem they given you 3.5 and area square plates. What is the square area of square? That is A square. So 100 into 100 to 10 power minus 4 divided by D there. 2 millimeter apart there. We have find out the capacitance. Then next one we can see about the charge there. Q equal to CV. Potential gradient is nothing but electric field E. Potential gradient is nothing but electric field E there. So E equal to what you will be having? V by D. And the next one what they have asked us? Flux density. Flux density is nothing but E equal to D equal to epsilon E. D equal to what you will be having as epsilon E there. So that's one what we will be having as that potential, electric flux density there. So the next one model problem we have that one. Parallel plate capacitor 50 centimeter and 50 centimeter separated by 5 centimeter in air. We have to find out the capacitance, energy stored and energy density. We have to find out C value, energy stored WE and energy density capital WE. So what is the capacitance formula? C equal to epsilon naught epsilon R A by D, as we have seen in the last problem. See, they are given with parallel metal plates. So it corresponds to parallel plate capacitor. If they are given with coaxial thing or with the spherical thing, we have to use that capacitance formula. In the last problem also they have seen they are given with the parallel metal plates. So that we are going with the capacitance of a parallel capacitor. So here you will be having C equal to epsilon naught epsilon R A by D there. Okay, so you will be having C equal to 1 point. If you substitute that value, you will be getting the capacitance formula there. Then energy. What is the energy stored in capacitor? Of CV square. Energy stored in capacitor, what will be having it as? Of CV square. They are given with potential value. Capacitance value just now we have find out. So energy potential we will be getting it as WE equal to this one. Then energy density equal to half epsilon E square by 2. Half epsilon E square by 2 here. So first we are finding out the electric field equal to V by D. So E value you know that one. Now if you substitute that one, you will be getting the WE value. Epsilon naught epsilon R E square by 2. So E value if you substitute, and you can find out the energy density part. Like this we can see with this one, and this one, this problem relates with the parallel plate capacitor with two dielectric mediums. So far we have seen with one dielectric medium, and this one resolves with the two dielectric mediums here. So if the diagram I have shown for your easy understanding, over one plate and another plate, the top we have one plate and the bottom we have that another plate, we have two dielectric mediums. What will be if you have two dielectric mediums there? That the formula you will be having as C equal to A by D1 by epsilon 1 plus D2 by epsilon 2. And the clue what they have given us, each occupies half of the space between the plates. Half of the space between the plates. For that we have to derive this one. D1 equal to D2 equal to D. So total distance is D1 plus D2. So either you can have D equal to 2D1, okay, or either you can do or D2 equal to D1 by 2 there. So I am substituting D1 equal to D by 2 here, and D2 is also equal to D by 2. So substitute the values of here, you will be getting the capacitive part here. Okay, already we know about the epsilon R value and all these concepts. Area value you know, distance value you know, epsilon R1, epsilon R2, all values you know that. Only that we have to derive which is D. What is the formula for D1 and D2? From the clue, that's what I underlined that one. Each occupies the half of the plates there. Each occupies that half of the plates. From that we can find out the capacitance. So now we have find out D1 and D2. Substitute that value, you will be getting the capacitance. Okay, pa. So far in today's class, we have seen about this potential. The last three classes we have started with the electric field, and we have seen about the potential in the gate program. Then the later on classes we can go with that magnetic field. We can go with that magnetic field concept, and we can see with rest of the things in the later on session. Thank you for attending the session. You can wind up. Thank you.